Our Earth presents an infinite number of questions. How, why, when did things become the way they are? To find answers to these questions, we use the scientific method. First, we observe the complex world about us. We ask of each thing we see, how, why, when. And eventually, possible answers to these questions are found. Secondly, we test these possibilities by gathering evidence. Enough evidence for one answer to be accepted. A mystery, a possible answer. A great amount of study and hard work. The scientific method that has produced many answers to questions we've had about our universe. One question has to do with the Earth's land and water. Have the continents and oceans always been located where they are now? If not, how and when did they move? By applying the scientific method, a new theory has developed. The theory of continental drift. At the turn of the 20th century, a German geographer named Alfred Wegener was studying a map of the world. In examining the Atlantic Ocean, he noticed that the coastlines of North and South America and Europe and Africa were quite similar. Is it possible that the American continents were once part of Europe and Africa? 3 years later, Wegener introduced his theory of continental drift, convinced that at one time all continents were united in a single landmass. He called the land Pangaea. To further support his theory, Wegener looked at fossil and rock similarities found on either side of the Atlantic. But this was not enough evidence for his theory to be accepted. In the 1950s, a group of English geologists uncovered new evidence while studying the Earth's magnetism. The Earth, like any other magnet, has a magnetic north and a magnetic south. The magnetic north for the Earth is located on the Canadian island of Bathurst. This is not the same as the true north, which is almost 1,000 miles away. The true north is the point on which the Earth rotates and is a permanent position. The magnetic north, however, appears to have changed its location over millions of years. It was while locating these positions that geologists uncovered evidence for continental drift. To find these positions, they could not use a magnetic compass, for it only tells the magnetic north today. But they could use rocks. Lava is liquid rock that is pushed to the surface of the Earth. Contained in lava is an iron compound called magnetite. When lava cools below 1,000 degrees, it solidifies. When it drops below 600 degrees, the magnetite in the lava becomes magnetized in the same direction as the Earth's magnet. If we can find this direction in these old lava flows, we can locate magnetic north when this lava was formed. These geologists show how this is done. First, the present position of magnetic north is marked on the rock. Then the orientation of the rock is measured. All of this data is carefully recorded. Finally, the rock is broken loose and taken to a laboratory. Here, a piece of the rock is cut into a usable size. This is called coring. Then the core is tested. This highly sensitive instrument detects magnetic traces. With it, we can learn the direction of the Earth's magnetic field when the rock was formed. Cores from North American rocks indicate that magnetic north 500 million years ago was in the East Pacific. Rocks from Europe and Asia were also tested, but they show magnetic north 500 million years ago to be in the middle of the Pacific, 3,000 miles east of the American magnetic north. Since it is physically impossible to have two magnetic norths, what would happen if we move the two poles together? If we move a pole, we must also move a continent. It is evident that the continents must have drifted. But how? In the late 50s, the Navy began exploring the ocean floors. The Atlantic Ocean was mapped, revealing an enormous ridge, a ridge as high as the Rocky Mountains and hundreds of miles wide. It was named the Mid-Atlantic Ridge. The Pacific Ocean was also mapped. Off the coastlines of the continents, a set of trenches was found. The deepest trench, the Mariana, plunges 7 miles down. What caused the ridges and trenches? In 1961, while studying these maps, two geologists, Drs. Dietz and Hess, independently proposed the same remarkable idea. Looking at a cross-section of the Earth, we see two layers, the lithosphere, composed of hard, brittle rock, and the asthenosphere, composed of a soft, pliable type of rock. The trench, Dietz and Hess proposed, is formed by the lithosphere dipping down into the asthenosphere. At another place on the surface of the Earth, the lithosphere spreads. Molten rock from the asthenosphere pushes up, forming a ridge. The overall result is a continuous moving plate where new crust is created at a ridge and old crust is destroyed at a trench. If a continent happened to be part of this plate, it would move along with it. Seafloor spreading introduced an entirely new way of looking at the Earth called plate tectonics. Using the ridges and trenches as boundaries, the Earth can be divided into 10 major plates, all moving on the Earth like slabs of ice on water. But how can we be sure this is really happening? What evidence is there? On the ocean floor are layers of sediment composed of sand, mud, and dead sea organisms. If the seafloor is spreading, new sediment must be settling on the recently formed ridge. Thus, on either side of a ridge, the bottom layer of sediment should grow older as we move away. But how can we find the age of this bottom layer of sediment? In 1968, the National Science Foundation funded a deep-sea drilling project. A ship, the Glomar Challenger, was built and equipped to drill into the ocean floor. Using miles of pipe, drilling was carried out at regular intervals across the mid-Atlantic ridge, bringing up cores of the bottom layer of sediment. A laboratory on the ship enabled scientists to date each core as soon as it was drilled up. From the Atlantic, the Glomar Challenger continued on to other oceans, but not before demonstrating that the seafloor is in fact spreading. Cores that were drilled near the ridge were less than 1 million years old. However, they became progressively older as we move away, reaching 200 million years near the continents. In 1970, using information gathered from seafloor spreading, rock magnetism, fossil and coastline similarities, the first maps were made attempting to show accurately how the continents have drifted. 200 million years ago, all land was one, Pangaea. Spain and New York touched at the equator, and India bordered Antarctica. At that time, dinosaurs were roaming the earth. By 180 million years ago, Pangaea had split in two parts, Laurasia and Gondwanaland. By 65 million years ago, South America had separated from Africa, and India was moving north. This is how the continents look today. North and South America have connected, and India has collided with Asia, the crunch creating the Himalaya mountains. Slicing through California is the San Andreas Fault. Here, two plates are moving past each other. The Pacific plate moving north, relative to the North American plate. While the plates move continuously, the fault does not. Stress builds up until it exceeds the strength of the rocks. The rocks break, and there is an earthquake. Most earthquakes occur at the ridges, the trenches, and places where plates are colliding or slipping past each other. Plate tectonics also helps explain the large number of volcanoes in the Pacific. Most of these volcanoes are near oceanic trenches. The lithosphere, dipping down into the asthenosphere, causes the asthenosphere to melt. Molten rock rises to the surface. Volcanoes erupt. Mountains are formed. We have seen how the scientific method has been applied to the mystery of continental drift. We know more about our Earth, yet curiously, the number of mysteries has not decreased. For example, the drift from Pangaea to the continents as we know today has taken 200 million years, long enough for a mountain to form and erode away 10 times. Yet, looking at this time on a graph, where one pole represents the formation of the Earth and the other today, we see that 200 million years is but a fraction of the Earth's history. What was there before Pangaea? How was it formed? And what forces caused Pangaea to split apart? Albert Einstein once said, "As a circle of light increases, so does the circumference of darkness around it."